Right. So, welcome to 56th lecture. This is the last week of this course. So, we are very pleased to have entered the last week, and this is the first lecture of last week. Uh, so today we'll do further example of Lindblad equation, which is we'll do block equation in NMR or ESR. That's a very famous equation, but so whereas block equation was phenomenological, we will derive it using the Lindblad mechanism. Very good. So we saw in the last example that we did spin lattice relaxation. So as well as like we had the decay where we observed that the relaxation decays from spin 1 to spin 0. And today we are doing the NMR ESR kind of example. The Hamiltonian is H equal to minus of omega naught by 2 sigma z. We are again taking H bar equal to 1. Okay, so we have this equation from the last time. Now we introduce three Lindblad operators. Okay, and they are as follows. So we have L plus equal to we have L plus equal to gamma plus 0 1 0 0, L minus equal to root over gamma minus 0 0 1 0, and we have Lz equal to root over gamma z. In many cases people use gamma 1 gamma 2 gamma 3 as well. So 1 0 0 minus 1, which is basically the sigma z matrix, right? So now your L plus describes the relaxation process, the relaxation process 1 to 0, which was like kind of a spontaneous emission we covered in the last lecture. And your L minus describes excitation process, the excitation process where the system goes from 0 to 1. Okay, right. Now we will very quickly do the okay. Yeah, LZ captures the dephasing process. Okay. So basically, this is without any energy transfer. In other words, this is decoherence without dissipation, without any energy transfer. Okay, very good. So your Lindblad equation now becomes, the Lindblad equation which we did in the last example also. So the Lindblad equation now becomes so Lindblad equation was del rho del t equal to 1 by so basically minus I by h bar. We are taking h bar equal to 1 h rho, which is the Schrodinger evolution, plus so sum over k lk rho lk dagger plus anti-commutation, half of anti-commutation lk dagger lk rho. Okay, so that becomes del t. Now rho is like rho naught rho 0 0 rho 0 1 rho 1 0 rho 1 1 is equal to I omega naught 0 rho 0 1 minus of rho 1 0 0 and plus your gamma plus rho 1 1 minus of rho 0 1 by 2 minus of rho 1 0 by 2, and this is minus of rho 1 1, okay, plus gamma minus of rho 0 0 minus of rho 0 1 by 2 minus of rho 1 0 by 2, and this is rho 0 0 plus gamma z, and that's 0 0 minus 2 rho 0 1 minus 2 rho 1 0. All right, so this is your if we continue using the equation numbers from the last time. Okay, let's say this is equation number 1 for today. So let us find the equilibrium values. So let's find the equilibrium values, rho equilibrium of rho of t. Okay, this is your rho of t. Okay, I should use another color, right, to separate. Right. So, right. So now the off diagonal elements, coherence term goes to 0 as t goes to infinity. Okay, this is expected from the previous calculation also. So now, so this is the condition for equilibrium also. So for the diagonal elements, the condition, so for, let me change the color. For diagonal elements, the condition del rho del t equal to 0 is the steady state condition. Okay, so this is the steady state condition. Very good. So this leads to gamma plus rho 1 1 gamma plus rho 1 1 equilibrium equal to, sorry, minus gamma minus rho 0 0 equilibrium equal to 0. So this condition is the condition of detailed balance. So basically, so in other words, like gamma 1 1 equilibrium upon gamma rho 0 0 equilibrium by so rho 1 1 equilibrium by 0 0 0 equilibrium equal to, so your gamma minus by gamma plus. Okay, so that's your detailed balance condition. From statistical mechanics we have studied detailed balance condition, or condition of detailed balance, right? So very good. Next page. So what is this? So basically this is the excited state population. Okay, let me change the color. This is the excited state population, and there is a ground state population. Okay, so ground state population, POP, right? So ground state, or I can also say as GS, ground state population, right? So now the equilibrium condition. So notice that the equilibrium condition follows the Boltzmann distribution, condition of detailed balance distribution. Okay, so in other words, so therefore I have rho 1 1 equilibrium by rho 0 0 equilibrium equal to gamma minus by gamma plus equal to e to the power minus of omega naught by kt. So this is the equation number 2. Okay, so that's effectively I am using h bar equal to 1. So now the boundary condition. So the boundary condition is rho 0 0 at t equal to 0. So initially it's equal to rho 0 0 0. Rho 1 1 at t equal to 0 is rho 1 1 of 0. So therefore the solution of this equation, solution of the Lindblad equation, equation number 1. So solution of equation number 1 is rho 0 0 at a time t is equal to rho 0 0 equilibrium plus rho 0 0 at 0 minus rho 0 0 equilibrium e to the power minus of t by t1. Now this solution just follows the last lecture, very very similar. We have rho 0 1 of t is equal to rho 0 1 e to the power I omega naught minus 1 by t2, the same. Okay, I'll define what is t2 times t comma rho 1 0 of t is equal to rho 1 0 e to the power minus, sorry, e to the power not minus, e to the power inside minus I omega naught minus 1 by t2 times t and rho 1 1 and your rho 1 1 of t. So one thing, yeah, so rho 1 1 of t equal to rho 1 1 of equilibrium plus of rho 1 1 minus rho 1 1 equilibrium e to the power minus of t by t1. So the off diagonal elements gives you t2 and diagonal elements t1. And what are t1 and t2? t1 and t2 are as follows, where your t1 inverse is equal to gamma plus plus gamma minus, and t2 inverse is equal to gamma plus plus of gamma minus over 2 plus 2 gamma z. Okay, so this is your spin lattice relaxation. And this is your spin relaxation in the second page. Okay, so that is it. So it is expected that, so now it is expected that L plus process involves emission of RF photons. RF is radio frequency photons. Okay, and L minus is involves absorption of photons, RF photons. Okay, so this is kind of clear. So now now let's assume right now let's assume based on this assume like gamma plus is equal to some gamma into 1 plus n omega naught, where your I'm coming to that, and gamma minus equal to gamma n omega naught, where your n of omega is equal to 1 is the is the boson distribution, 1 minus of e to the power beta h bar omega, where your beta is 1 over kt, right? So this is nothing but your this is the Bose occupation number, okay, because photons follow Bose statistics, so that's why we have this. And h bar omega naught, h bar omega naught, and this is a minus h bar omega naught, right? So boson statistics. So then your T1 and T2 are given as, so T1 inverse is equal to gamma e to the power omega naught by kBt, because beta is 1 over kBt, cot hyperbolic omega naught by 2 kBt, and your T2 inverse is equal to T1 inverse by 2 plus 2 gamma z. Okay. So T2, so notice that T2 may be shorter than T1 if pure phase damping, so gamma, so basically sigma z gives you the phase damping. Pure phase damping process is fast, that is gamma z is large, as is frequently the case. Okay. In real life, T2 is actually less than T1. Okay. Very good. So with that, we wind up this example. So I just want to, so we have about 12 minutes left. So I just want to introduce a concept called the generalized measurement. It may not be possible in the 12 minutes that we have, but I'd like to go fast. And right, so generalized measurement. So it is actually not too disjoint. So the concept of generalized measurement is not too disjoint from what we have been doing already. So let's just very quickly have a look at this. So this is a continuation of this lecture, but it's a new topic which is called generalized measurement. And a quantum computation course cannot be completed without measurement. So we all know about projective measurements. So projective measurements are a special kind of generalized measurement. So let's projective measurements are basically you are projecting in, say, x-axis, projecting in z-axis. So those kind of measurement. Okay. And just a minute now, this out of charge. So therefore, so a generalized measurement, is described by a set of operators mi. So basically these are set of measurement operators mi, not necessarily self-adjoint means Hermitian join, but that nevertheless satisfies the completeness relationship, which is sum over I, sum over I, M I dagger Mi is equal to identity. That's somewhat like the cross operators, right? So this is, let's say, equation number one, right? So now, so if the state vector, okay, so supposing just if the state vector uh, of the system before measurement is, say, psi, okay, so is psi, then so if we then with the probability Pi is equal to psi Mi dagger Mi psi, that's equation number two. With the probability, the measurement outcome gives an outcome I, okay, or which is corresponding to the eigenvalue lambda I, and post measurement the system is in the state psi I prime, and I would normalize this, so this is simply Mi times psi I, so the state should be in Mi times psi I, but I need to normalize this, so that would be psi Mi dagger Mi psi, okay, this is equation number 3, right? So now so equation 1 certifies that the probability PIs add up to 1. Let's just quickly examine equation 1. So this condition basically says that my probabilities add up to 1. Okay, right? So therefore, like sum over I, Pi is equal to sum over I psi Mi dagger Mi psi. So that's simply so if I, okay, so I pull that, so the summation I inside, so this equal to identity, and therefore this adds up to 1, because psi bracket will be 1 because it's a normalized state. Now projective measurements which we are familiar with, which is basically part of foundations of quantum mechanics, which people would have studied in an earlier course of quantum mechanics. So projective measurements are a special case of generalized measurement. Okay, so the idea is that measurements. Okay, so and also projective measurements are orthogonal. So measurements where the operators mi are orthogonal projectors projectors. So just to give an example of orthogonal projectors is basically so you see, let's say I have the state like these, this, okay, or one. So these are orthogonal projectors, and they will project the system onto the, say, along the z-axis, or one of the states, which is basically along the z-axis, along ket 0 or ket 1. So continuing the definition, so the measurements where the operators mi are orthogonal projectors, that is mi dagger equal to mi and mi mj equal to delta ij. So then the completeness relationship, then the completeness relationship, relationship reduces to sum over I mi equal to identity, and your sum over I pi equal to identity, because your PIs are the projections. Okay, so projective measurements, so therefore projective measurements are equivalent to generalized measurement measurements provided ancillary qubits are added. Okay, so this is like the extension of Hilbert space, or purification extension of Hilbert space, or purification which we did in terms of the cross operators, right? So extension of the Hilbert space. So external qubits are added. So just recall, we don't have much time. Let's see, recall a system and environment prepared in a product state product state, say psi and E naught. So this was similar to, so let me just similar to your psi and 0. Okay, this is environment and this is system, which we did before. So these are acted by a unitary operator to U in the larger Hilbert space, which is HSE, system and environment, and which applies, okay, half an hour over, I'll just extend by a couple of minutes, applies an operator mi on the system and not the environment, and and at the same time put the environment to the EIs or to the EIs of for various I's. So I'm deliberately choosing a different notation. So basically your full system plus Hilbert system plus the ancilla, basically Hilbert spaces U psi E naught is equal to sum over I mi your psi times Ej. Ej's are the environmental thing. This is equation number 4. Okay, so I just want to, so I will stop here, but just want to basically draw your attention to a couple of things. So in the cross representation, so just a comparison in cross representation, we had seen that U acting on psi times 0 is equal to sum over I, sum over k, ek psi times k. Okay, so if you recall this, so these are on the environmental Hilbert space. Okay, these are on the environmental Hilbert space. This is on the system Hilbert space. Okay, so this was effectively similar, except that here the MIs, EKs are replaced by the M's, and the K's are replaced by EJ, but picture is same picture, equivalent picture. Okay, so if you just recall, just bear with me for one more minute. So if you just recall that our rows were U psi E naught psi U dagger. Okay, remember, and this is the row E type thing. Okay, and this is basically the ket bra hope full psi, so the capital psi, which is in the system, and this thing, right? So the fact that this is normalized, the fact, one moment, so just the fact that the psi's must satisfy normalization condition. I have psi E naught U dagger U psi E naught equal to sum over I comma j psi EI M I dagger MJ tensor identity, because there will be a tensor which is acting on the psi j's, psi and EJ, and this is simply psi sum over I dagger mi, because of the orthogonalization of EI and EJ, I have psi is equal to 1. So since psi is arbitrary, I have sum over I mi dagger mi is equal to identity. So identity in the system Hilbert space, HS. All right. So I will stop here and I will continue the discussion in the next class.